Okay, again, this should be not circumference and arc length. It should be sample spaces and probability. Okay, so a couple keywords we need to talk about first. The first one is called, is just experimental probability. And actually it was supposed to be probability experiment, but I mixed that up as well. But it's an action or trial that has various results. Okay, it's something that we can actually do to figure out the results. All right, an outcome is the result of experimental probability. Okay, so we'll be talking about outcomes today. All right, an event is a result of one or more outcomes. Okay, so we have multiple outcomes. Well, that becomes an event. And then sample space is just a weird word or weird way to say it's the set of all possible outcomes. Okay, and set is a math word to say list. So a sample space is just a list of all the possible outcomes that we can possibly come up with. All right, so example 1, it says you flip a coin and roll a 6-sided die. How many possible outcomes are in the sample space? All right, well, you flip the coin first. What are the two options that you can, or two outcomes from flipping a coin? Heads or tails, right? So one option is a heads, and the other is a tails. I'm kind of making like a tree or a table or a flow chart, if you will, of all the possible outcomes. So let's go. So let's say I get heads when I flip this coin. Now I'm going to grab a die and I'm going to roll a die. 6-sided. I think I've got 6 opportunities that I could roll on that die, either a 1, 2, 3, 4, 5, or 6. So from the heads, I have 6 things coming from that heads outcome. And that's rolling a 1, rolling a 2, rolling a 3, a 4, a 5, or a 6. Okay, if I roll a tails and then I roll the dice, did I say roll a tails? If I flip a tails and then I roll a die, I'm going to have 6 chances or 6 possible outcomes that I could get from that die. Now, list all the possible outcomes. Well, first of all, it says how many possible outcomes are in the sample space? I think there's 12. There's 6 over here coming from the heads, and there's 6 over there coming from the tail. So there's 12 possible outcomes. And it says we need to list them. Okay, well, how do we list them? What are those, Beth? Yeah, I'm going to abbreviate and just call it H1. Heads 1. That's a possibility that we could get, a possible outcome. Heads 2, heads 3, heads 4, heads 5, and heads 6. Do the same thing with tails. Tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. Questions there on example 1. Okay, next key thing here is talking about probability of an event. Okay, the probability of an event is the measure of the likelihood or chance the event will occur. Okay, so the probability of an event is just, hey, what are the chances of this actually happening? Okay, and so theoretically, a theoretical probability is, basically by the books. Okay, what's the probability that this is going to happen? Okay, now in experimental probability, that might always match up, but by theoretical probability is, hey, what are the chances? What's the likelihood? Okay, and that is the number of favorable outcomes What's favorable mean?
Likely.
What, Chris?
Likely.
Maybe not quite likely. Talk to the person next to you. What in this instance, what does favorable mean? Go. Let me write the bottom here. It's the total number of outcomes. And as I asked that question, what does favorable mean in this instance? I heard a lot of people say it's what's most likely to happen. And I get why you think that, most favorable. But in this instance, favorable means what's the outcome that we want to happen. Okay? So if I could go back to that sock example I kind of referred to at the beginning of the lesson, I've got a certain amount of possibilities that I can pull out. That's the total number of outcomes. If I want to say, hey, I want to draw a red sock, well, how many red socks are in there? Does that make sense? So that's what we're trying to get to, or what's our goal. That's our favorable outcome. Maybe it's a red socks, maybe it's a blue marble, whatever it may be. And the denominator in the bottom is the total number of outcomes. Example 2. A student is taking a quiz randomly, a student taking a quiz randomly guesses the answers to 4 true-false questions. I think we've all been there, right? What is the probability of the student guessing exactly 2 of them right? Dean, what do you think?
25%.
25%. Why do you say that?
Because the first one would be 50, because it's only 2 answers.
Okay.
But then you have the second one, which is also 2 answers, which would also be 50% of each one. But getting both of them right, you would have to divide the first one by 2.
Okay, that's a thought. That's an idea. Joe, what do you think?
But he could also get exactly 3. He could get 3 of them right.
He could get 3 of them right. He could get all 4 of them right, couldn't he? Or he could get none of them. Or 1. Chris?
So the number of favorable outcomes would be 2, and then the total number of outcomes would be 8, so wouldn't it be 2 divided by 8, which would equal 0.25.
Is that what you said, Dean? You said?
No, I said 50% divided by 2.
So 0.25. Let's think about this for a second. I think we have a few different outcomes. There's a probability he's going to get 0 of these right. Okay? And that's usually me when I start guessing on true false. There's a chance he's going to get 1 of them right. There's a chance he's going to get 2 of them right, and that's our favorable outcome. That's what we're looking for. There's a chance he could get 3 of them right, and there's a chance he could get 4 of them right. Now, if he gets 0 of them right, I'm going to use an I for incorrect and a C for correct, okay? If he gets 0 of them right, aren't they all incorrect? There's only one possible outcome for getting them all wrong. That's incorrect, 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 incorrect. Okay? Now, if he gets one of them correct, he could have gotten the first one correct, could have gotten the second one, the third one, or the fourth one. He doesn't know. So, I'm going to put correct, incorrect, incorrect, incorrect. That's a possible outcome. He could have got the first one right and the rest wrong. Or he could have gotten the first one wrong, the second one right, and the third and fourth one wrong. He still got one right, but the problem he got right is now changing. That's a possible outcome. He could have gotten the first two wrong and the third one right, or he could have gotten the first three all wrong and the last one right. So there's one possible outcome to get 0 of them right, and there are 4 possible outcomes to get 1 of them right. How many outcomes are there going to be to get 2 of them right? Let's talk through this. To get 2 of them right, well, how are we going to do this? He could do the first 2 right and then the last 2 wrong. He could have gotten the first one right, the second one wrong, the third one right, and the fourth one wrong. Guys, I think it's pretty good to have a procedure on what we're doing. Here's the procedure I'm using. I'm going to keep the first one correct, and I'm going to move the second one. Okay? Well, there's ICU. And then, there's a chance he could get the first one right again, the second one wrong, the third one wrong, and the fourth one right. So, with getting the first one right, those are all the possibilities of getting the first one right. He's going to get the first one right, the second one right, the third and fourth wrong. He's going to get the first one right, the second one wrong, the third one right, and the fourth one wrong. He's going to get the first one right, second and third wrong, fourth one right. Okay? Now, let's talk about the chances, the possible outcomes if he gets the first one wrong. So if he gets the first one wrong, he could get the second and third correct, and then the last one wrong. He could get the first one wrong, the second one right, the third one wrong, and the fourth one right. Are there any other possible outcomes if he gets the first one wrong and the second one right? Let me rephrase the question. Are there any others with him getting the first one wrong, other than these two, and the second one right? I don't think so. These are only other outcomes, only 2 outcomes to get the first one wrong and the second one right. Okay, but that's, what's my question? Are there any other options to getting the first one wrong and the second one right? Does that make sense, Elizabeth? The first one wrong, second one right, those are our 2 options. But like you guys said, he could get incorrect, incorrect. So he could miss the first 2 and get the second 2 right. I think that's all of them. Anyone's mind blown? Okay, that's good. 6 possibilities of him getting 2 of those multiple choice corrections or questions correct. Now, for him to get 3 of them correct, think about that one on your own. Go. All right, what are our options? Carson?
C, 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 I,
C, 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 I. Chance to get all three, the first three correct and the last one wrong.
CCIC.
C, C, I, C. So the first two correct, the third one wrong, and the fourth one correct.
CICC.
C, I, C, C.
And then ICCC.
And then I, C, C, C. You guys notice how Carson didn't just bounce around? It was kind of a method to what he was doing. Kind of moved it over every time. I think that's important. I tried to. Maybe you guys didn't follow what I was doing over there, but I tried to have a method to the madness there as far as where I was placing things, because if you just start throwing out options, you're going to lose track of a possible outcome or two. All right, and the last thing, a possibility of him getting all four of them correct would be correct, correct, correct. So I have 6 outcomes here, which is our favorable outcomes. That's what we're looking for. We've got 4 of them there and 1 there. So what we need to do, what's the probability of the student guessing exactly 2 of the answers right? We need to put our favorable outcomes over the total. Now, one thing I want to talk about right now is this notation here. So P, a capital P stands for the probability. So we're looking for the probability of something. And it's in this case, it's 2 correct answers. Okay, so you'll see that P and then parentheses, hey, the probability of this event. So in this case, it's probability of 2 correct answers equals the number of favorable outcomes, which is how many? There's 6 of them. 6 possible outcomes of getting 2 correct over a total of how many? 16. So 6 out of 16. That can be reduced, right? Take a 2 out of each and I get 3 out of 8. If I take 3 divided by 8, what is that as a decimal? What, Allie?
37.5. Or it's 0.375.
0.375. So a 0.375% chance of it happening, or I should say a 37.5% chance of it happening. Questions or animosities there? Okay, top of the next page. It says when 2 6-sided dice are rolled, there are 36 possible outcomes as shown. So if you roll 2 dice like you do in Monopoly and a lot of other board games, there are 36 possible outcomes. Find the probability of each event. All right? Find the chance, or this event, the sum is not 6. Now one thing I want you guys to understand, the probability of something to happen is going to be between 0 and 1. Would you guys agree there? It's like a percent chance, just like on the last time, it was 0.375. It's going to be between 0 and 1. Okay? So I think there's a lot more not 6s. Excuse me. There are a lot more not 6s than 6s. Would you agree? I think it's easier to count the number of 6s than it is to count the number of not 6s. So what I'm getting at here is the probability of not 6 equals 1 minus the probability that it is 6. Does that make sense? If I said, hey, the chances of us having a free day today is 25%, what's the chance of us not having a free day? Well, it's 1 minus the chance of us having a free day. So 75%. So the chance of not rolling a 6 is 1 minus the probability of rolling a 6. Now, why are we doing this? So I don't have to count all the not 6s. So let's find the number of 6s here. And if you circle these, do them lightly with a pencil because we have a second part to this question. So let's find the 6s. Isn't that a 6? Again, do this lightly because we're going to erase them because we've got a second part here. That's a 6. Up 1 over 1, that's a 6. 3, 3, that's a 6. 4, 2, that's a 6. 5, 1, that's a 6. Are there any other 6s that I'm missing? No. So this is going to be 1 minus favorable outcomes in this situation are 6s, which are how many? 5 out of a possible 36. So if I'm going to subtract fractions, what do I need again? Common denominator. So I'm going to rewrite 1 as 36 over 36, because 36 divided by 36 is 1, minus 5 over 36. 36 minus 5 is 31 over 36. So the chances of not rolling a 6, 31 over 36, which I guess if you get a decimal there, what is that, Joe?
0.86 and then 1 repeating.
861 repeating. So about 86% chance of you not getting a 6. Questions on that? Okay, next one. Find the sum, or the probability that the sum is less than or equal to 9. So the probability the sum is, I'm going to use inequalities here, less than or equal to 9. Again, that's going to be quite a few. So we can do 1 minus the probability of what? Greater than or equal to? No. So just greater than 9. Because this is less than or equal to 9. There's either two things. It's either going to be less than or equal to 9, or it's going to be greater than 9. So let's find all of the possible outcomes that are greater than 9. Well, here's 9. Here's 9. So this diagonal row all equals 9. We don't want that because that equals 9. That's in this. We want everything greater than 9. So that's going to be 1, 2, 3, 4, 5, 6. So the probability of less than or equal to 9 is going to be 1 minus the probability that's greater than 9, which is 6 out of 36. So again, I'm going to call this 36 over 36. And 36 minus 6 is 30. So 30 divided by 36. That can be reduced, can it? 5 over 6. Or what's that decimal? 0.83 repeating with the 8 or the 3? No, just 0.83. Okay.
Isn't that not what we're supposed to find though?
Say it again?
Aren't we supposed to find the sum that is less than or equal to 9? Or no?
I think we did that. Because this is the probability that it's greater than 9, which is small. And I took 1 minus that. There's our probability that it's going to be less than or equal to 9. Now, could we have just calculated all of the ones that are less than 9 or equal to 9? Done it that way? Yes. And we would have gotten 30 of them. Just a way to think differently about probability. I've got two more. The second one's easy. It says you throw a dart at the dartboard. Your dart, put an R in there, your dart is equally likely to hit any point inside the square. Okay? So it's not like, you know, it's a funky dartboard or the floor is unlevel, so you're more likely to hit the right side. The chance you're going to hit, it's even throughout the board. Are you more likely to get 10 points or 0 points is the question. How in the world are we going to do this? Area?
Of the square, of the square, of the circle.
Okay, now is 0 points is only the light blue, right? So we're going to have to find the area of the light blue stuff. And we're going to have to find the area of the 10 points, which is 10, or the middle part, the pink part. Let's start with the pink. Okay, so 10 points. The likelihood of getting 10 points is again, what's our favorable outcome? Well, it's the pink part divided by the total. So we need to find the area of the pink part divided by the total area. That will get us the probability or the likelihood that we're going to get 10 points. So the pink part, that's a circle. What's our radius? 3. What's the formula for the area of a circle again? Pi r squared. It's not 2 pi r. What's 2 pi r? Circumference. A lot of people mixing those up on the test. So pi r squared, so pi times my radius, which is 3 squared, divided by the total. Now, the total is this rectangle, or square I should say. What are the dimensions of this square?
6 by 6.
9 by 9?
18 by 18.
Would you guys make up your mind?
18 by 18.
18 by 18. So this is 3. That's 3. That's 3. Well, that's only the radius. On the other side, that's 3. That's 3. That's 3. So it's actually 18 by 18. So this is going to be 18 times 18. So this is going to give me 9 pi. And 18 times 18, is that 324? 324. So now I can take 9 pi, divide by 324, and that will get me the probability or the likelihood that I would get 10 points. What do you get there? Point. Let's go with, I don't know how close this is going to be. Let's go out of three or four decimal places. Do we agree there? 0.872.
You have to put parentheses around all 9 pi.
Only 872, that's what I
You have to
got.
put parentheses around 9 pi.
Point 0.
3.
Sure. Just a few more because I don't know how close this is going to be. So now to get to 0 points, well, that's going to be the light blue over the total. Now I already know the total. That's 324. That's going to be the same. But how are we going to find the shaded or the light blue part? The square, which is 324, right? Minus the big circle. Minus the yellow circle and everything that's inside of it. So what's the radius of the big circle? 9. So the area of that big circle is going to be 9 pi. So you need to take 324 minus 9 pi. Oh, shoot. Yeah, we better do 9 squared pi, which is 81 pi. Never mind. 324, which is the total of the square, minus 81 pi. And then get that number, divide it by 324, because that's our total. And that will get us the likelihood of getting a 0. Point 2,146. So are you more likely to get 10 points or 0 points? 0 points. Would you have guessed that, looking at the picture? Yeah, maybe. There's four blue parts, so that's important to keep in mind. Okay, and last question. You guys, I forgot to attach the table in the picture, or the thing. So whether you want to draw this in there to help understand it, or you can just watch up here. It says each section of the spinner shown has the same area. So same area of yellow, blue, red, and green. The spinner is spun 20 times. The table shows the results. So 5 landed on red, 9 on green, 3 on blue, 3 on yellow. Now, theoretically, what's the chances of the spinner landing on each color? 25%, 1/4. All right, so what are the chances of landing on blue? Well, the favorable outcome would be 1 out of a possible 4. So theoretically speaking, everyone's got an equal chance of landing on that color. Okay? It says for which color is the experimental probability of stopping on the color the same as the theoretical probability? So experimental, meaning, hey, we did the experiment, we ran the results 20 times. Which one is the same as theoretical, which is 1/4? So this is 5 over 20. This is 9 over 20. 3 over 20. And 3 over 20. Which one reduces to 1/4? The red one does.